Good afternoon, everyone. So we are reviewing Wetzel's Limnology textbook, edition number 4, chapter 4, and we will be focusing on subchapter 6, reservoirs. While much of our limnological understanding originates from natural ecosystems, it is also important to consider the special role of the millions of reservoirs that have been built to serve human purposes. These purposes include domestic water supply, irrigation, flood control, hydroelectricity, navigation, and recreation. Although humans have been building reservoirs for thousands of years, the pace and magnitude at which they were built increased in the last century. In 1950, there were approximately 5,000 large reservoirs in operations worldwide, and by 2018, that number had increased to nearly 60,000. While the bulk of the construction boom occurred in 5 countries, the United States, China, Spain, Japan, and India, large dams were established as a global phenomenon by 2000 and are now rapidly proliferating in previously undeveloped drainage basins, including in the Balkans and across the Amazon and Mekong River basins. Today, reservoirs are estimated to cover a new water surface area of over 300,000 kilometers squared and store more than 7,000 cubic meters of water, which represents about 1/6 of the world's total annual river flow. Smaller reservoirs and farm ponds are estimated to number in the millions. Reservoir characteristics. Reservoirs can be built in stream or less frequently upstream. In-stream reservoirs are constructed by damming a river valley. Water then accumulates behind the dam. Water released from the dam is typically regulated to manage incoming flows, such as for flood control or to support downstream water uses. Upstream reservoirs can constitute small artificial ponds built in valley depression where inflows occur by surface flows and/or seepage. Upstream excavation of soil for construction or mining can also result in reservoirs or artificial lakes, as these excavations can cut into the water table of groundwater aquifers or be filled with mining effluents, for example, tailing ponds, strip mining lakes, barrel pits, lakes, etc. Outflows from these excavations generally only occur by subaqueous seepage, evaporation, or breached levees. Large reservoirs bring about physical and chemical changes that influence aquatic biota in many ways and can be deleterious to human welfare and the environment. Most fundamentally, dams and their reservoirs alter the diurnal, seasonal, or interannual flow patterns, reduce downstream flooding, and are the main cause of the loss of fluvial connectivity found in natural river systems. As a result of the majority of the world's large rivers are no longer free-flowing, with unfragmented rivers primarily left in remote regions such as the Arctic or the Amazon and Congo river basins. Movements of diadromous and non-diadromous migratory fish species are impeded or inhibited. As they replace flowing with standing waters, reservoirs alter the chemical composition of the water they store and release. This includes changes in water temperature, oxygen content, and nutrient concentration, which in turn affect biogeochemical cycling processes. Reservoirs also impede sediment transport, thus affecting downstream fluvial geomorphology and aquatic habitat characteristics. Overall, the effects of dams and reservoirs can be felt far downstream, sometimes for hundreds of kilometers or all the way to the river delta. Due to their various effects, reservoirs can cause serious dislocations of traditional human societies, either by displacement or by indirect economic and livelihood changes. The newly created stagnant water body of reservoirs can contribute to the spread of certain diseases that rely on waterborne vectors, while they may reduce the incidence of others. Although reservoirs are often built to alleviate water scarcity, they can render cities ill-equipped to handle drought conditions or push water scarcity hotspots downstream, as upstream regions benefit from stored water to the detriment of those downstream. While large reservoirs number in the tens of thousands, millions of smaller reservoirs dot the landscape. Particularly in agricultural regions, an estimated 1.8 million small farm ponds in Australia store nearly 11 cubic meters of kilometer cubes of water, and more than 1 million dams fragment Europe's rivers, though not all of these create a reservoir. While large reservoirs have customarily garnered more scientific attention, the individual and cumulative effect of small reservoirs are now being investigated and found to be considerable zonation in reservoirs. As a result of the common linear morphology in a river valley, three distinct zones tend to develop along the longitudinal gradient of a typical medium to large reservoir: a riverine zone, a zone of transition, and a lacustrine zone. Each zone possesses unique and dynamic physical, chemical, and biological characteristics. The width of the river zone is often relatively narrow and depends on the river's geomorphology. Although water velocities decrease as the water enters the reservoir, advective transport by currents is still sufficient to move significant quantities of fine suspended particulates, silt, clays, and organic matter. High particulate turbidity commonly reduces light penetration and limits primary production. Loading of organic matter from allochthonous sources is high in proportion to water volume in the riverine zone. High decomposition rates often results in high consumption of dissolved oxygen, but aerobic conditions generally prevail in the shallow, well-mixed riverine zone. So let's look at this table here. Reservoir characteristics by surface area, size, class, and globally. All data from blah, 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 not including regulated natural lakes. So we have kind of like the same type of table that we just saw above, for example, for rivers. And so we have area size class, so we're between 0.1 and 1 kilometer squared. We have the number of reservoir, which takes the lion's share. Then we have 1 to 10, we have 10,000. And then for the very large reservoir, we have 46 between 1,000 and 10,000 kilometers squared. And then we have volume based. So for example, 1,000 to 10,000 of the large reservoir and surface area represents 2,072 kilometers by 10 to the 3 kilometers cube. And we have a total of 76,000 reservoirs and a total volume of 7,132 by 10 to the 3 kilometer cube. The average mean depth, they vary, although they are pretty shallow, 18.7 for the very large reservoir in meters. The larger reservoirs by volume, we have Lake Kariba, Bratskoye Reservoir, Lake Nasser in Egypt, Lake Volta, Karuni Reservoir, the Williston Reservoir, the Kwanoyarskoye Reservoir, the Zeskyoye Reservoir, the Kahora Bassa Reservoir, and then the Roberts Burasa Reservoir. Now let's look at the generalized zone along longitudinal gradients in reservoirs, which was just presented in the text. So first we have the riverine zone, so there's a river inflow here. We have the transition zone, and then the lacustrine zone, which is the lake-based zone. And then we have a dam, and then we have a temperature profile from 20 degrees at degree centigrade at the surface to 4 degrees C at the bottom of the reservoir. And then we have then this valve system that allows the water to be discharged downstream. And as in lakes, we have an epilimnion, a metalimnion, and a hypolimnion, which are layers within lakes based on depth. River water velocity decreases as energy is dispersed over water areas in the transitional zone. An appreciable portion of the turbidity load settles out of the upper water strata as a result. Decreased turbidity results in an enhanced depth of light penetration and increased rates of photosynthetic productivity by phytoplankton. Gradually, a shift occurs to an increasing percentage of total organic matter loading from phytoplankton and in some shallow reservoirs from rooted vascular plants. Within the lacustrine zone, characteristics become more like those of lake ecosystems. This portion of the reservoir often stratifies thermally and assumes many of the properties of natural lakes when it comes to planktonic production, nutrient limitation, sedimentation of organic matter, and decomposition in the hypolimnion. Stratification and water movement can be modified or complicated both spatially and temporally by hypolimnetic or bottom withdrawal of water from the reservoir at the dam. For a review of beneficial, look at this paper. Geomorphological differences between reservoirs and lakes. Reservoirs differ in significant ways from natural lake ecosystems, yet studies of reservoirs ecosystem also indicate many functional similarities between artificial and natural lakes, such as in the metabolic functioning and community interrelationships of the biota. Comparative analysis of the geomorphological characteristics and properties between natural lakes and managed reservoirs, including their integration within the river system, can thus be instructive to point out both structural differences and functional similarities in these ecosystems. A summary of comparable hydrological and morphological attributes is presented in Figure 4-21 and 4-6 in Table 4-6. Because reservoirs are typically formed in river valleys, the morphometry of the reservoir's water body reflects the nature of these valleys by being dendritic, narrow, and elongated. These physical characteristics affect biological processes in many complex ways, the most important of which are light and nutrient availability. Reservoirs for irrigation or drinking water are created predominantly in regions where natural lakes are sparse or unsuitable for human exploitation. In these regions, the climate tends to be warm and dry, resulting in relatively high evaporative losses that can outweigh precipitation inputs. Reservoirs for hydropower production include some of the largest artificial lakes in the world. Their demand-driven management for electricity production can result in highly fluctuating water releases to serve short-duration peak requirements, so-called hydropeaking, creating downstream flows that are in stark contrast to natural conditions. Given their purpose to collect and store water, many reservoirs are strategically built on large rivers. Therefore, the ratios between inflowing discharge and storage volume, for example, the water renewal rates of reservoirs, tends to exceed those of natural lakes. The larger rivers also exhibit higher energy for erosion and thus carry larger sediment loads. Since reservoir inflows are primarily channelized and often non-intercepted by energy dispersive and biologically active wetlands and littoral interface regions, water influxes tend to be larger, are more directly coupled to precipitation events, and carry dissolved and particulate loads much farther into the reservoir than would be the case in most natural lakes. These properties result in high, irregularly pulsed nutrient and sediment loading to the reservoir. As the reduced flow velocities inside the impoundment then cause sediment deposition, reservoirs generally serve as both recipients and collectors of riverine sediment loads. In consequence, the longevity of reservoirs can be very short, often less than 100 years, before their entire storage volume is filled with sediments. Water level fluctuations tend to be small and stable in natural lakes, and shoreline erosion is localized to wind-generated currents. In contrast, extreme and irregular water level fluctuations are common in reservoirs as a result of their specific flood inflow characteristics, in particular if built for flood prevention, and they are often short-term water storage and withdrawal dynamics. This has multiple effects on sediment loadings and causes a more unstable shoreline morphology. For example, reservoir drawdown events associated with irrigation requirements and hydroelectricity generation can lead to large areas of sediments along shorelines being alternatively inundated and exposed. These shifts between aerobic and anaerobic conditions enhance greenhouse gas and nutrient release. Ultimately, the water level manipulations can prohibit the establishment of productive, stabilizing wetlands and littoral plant communities around the reservoirs and interfere with microbiotic life cycles. Overall, this causes much reduced nutrient and physical filtering capacity compared to those of most natural lake ecosystems. Figure 4-21. Natural lakes are water fields, depression in the landscape that can vary in their inflow and outflow conditions. So here we have lake types on the left, and then we have reservoir types on the right. So lake types here, we have surface inflow and outflow. We have a lake that is getting water from groundwater, and then an outflow that is surface water. Then we have a lake that is getting water from surface, and then discharging water from to groundwater. And then we're getting a lake here that is groundwater flow, and then that is also groundwater discharge. Reservoir types. So we have a low-tick system that is dammed. A reservoir may or may not be formed. So here we have a dam. Pre-existing lentic system is further impounded by the addition of a control structure. So here we had a river, and we basically dammed the river to create a reservoir. Here we already had a lake, and so we're damming the lake to create a reservoir. And then we have completely human-created water bodies located outside of a river network. These impoundments may or may not have a control structure, like a dam, and may or may not have an outflow, for example, farm ponds, stormwater retention ponds, upstream storage reservoirs. And as we saw in the text, there's a fair amount of those. Climatic and anthropogenic effects. Climate change is altering the global hydrological cycle through changed precipitation inputs, increased snow and glacial melt, and overall increased evaporation rates. In addition, humans are modifying surface water flows either directly by extracting water for irrigation, industrial and domestic uses, or indirectly by changing land uses, which in turn affects runoff processes or both. These alterations lead to complex changes in global water availability and stream flow, which can ultimately cause the expansion, shrinking, formation, or disappearance of rivers and lakes, both in space and time. Furthermore, entirely new artificial water bodies are created by humans through dam construction. Overall, there has been a global net increase in permanent surface water between 1984 and 2019, with reservoir filling being the main cause. A similar net increasing trend has been found to persist for large natural lakes for the period of 1992 through 2019, which is mostly attributed to climate variation as well as long-term climate change. Examples of spatial expansion include some lakes of the Tibetan Plateau, which have grown since the late 20th century due to increasing precipitation, glacier and snowmelt, and permafrost degradation following rising temperatures at high altitudes. Occurs not all regions of the world are experiencing surface water expansion. Severe depletion of surface waters occurs, for example, in the Middle East and the Southwest United States. A striking example is the Aral Sea in Central Asia, which lost 79% of its water surface area between 1960 and 2007 due to upstream irrigation withdrawal. Air temperatures are rising at twice the average global rate in Arctic regions, and the thawing of permafrost is a main driver in both the disappearance and the expansion of lakes in high latitude areas. Overall, lake areas and numbers are increasing on continuous permafrost soils, which are permanently frozen soils that are thawing at the top only, whereas many lakes are permanently drained into the ground in regions with discontinuous permafrost soils. In addition, some high Arctic ponds, which have been permanent water bodies for millennia, are now starting to dry during polar summers due to increased evaporation. So let's look at a couple things here. First one is this table. Comparative geomorphological and hydrodynamic characteristics and properties among natural lakes and anthropogenic reservoirs. The shape, for example. The property is a shape. We have a column for property, a column for natural lakes, and then a column for anthropogenic reservoirs. So, for example, if we look at shape being one of the property, natural lakes predominantly circular to elliptical. In terms of the shape for the reservoirs, they are variable, often narrow, elongated, ovoid, dendritic, or triangular. The mean depth, moderate to high, mostly moderate for reservoirs. The depth gradient, deepest, usually remote from shoreline, shallow in riverine portion, increasing toward transitional and lacustrine zones. Drainage basin, lake usually central or in higher portion of drainage basin. Drainage area often small in comparison to lake area. Reservoir often at base of drainage basin. Drainage area large in comparison to reservoir area. Shoreline development, relatively low, stable, relatively high, static, astatic for reservoirs. Shoreline erosion and substrata distribution, localized, induced by wind-generated waves for lakes, extensive riverine by water currents, less from wind-induced currents in lacustrine zone. Sediment loading, low to very low in reservoir, with large drainage basin. Deposition of sediments, low, limited dispersal. High in riverine zone, decreasing exponentially down reservoir for reservoirs. Sediments suspended in water, turbidity, or known as turbidity, low to very low for lakes. High, variable, high percentage of clay and silt particles. Water level fluctuation, as you may guess, very small for lakes and stable, very large and irregular for reservoirs. Inflow, runoff to lake via tributaries and diffuse sources. For reservoir, most runoff to reservoir via river tributaries. Penetration into stratified water, complex. Flow is often directed along old riverbed valleys. Outflow, withdrawal. Relatively stable for lakes and highly irregular for reservoirs because of their function. Residence time, often long, relatively constant for lakes, 1 to many years. For reservoirs, often short, variable. Disruption of stratification with hypolimnetic withdrawal. So this is figure 4-22, which shows the long-term trends between 1992 and 2019 in water levels for 200 large lakes. Color indicates the rate of change, and the p-value indicates the significance of the trend. So when we have a significant trend, we have a higher circle here, or a 0.01, a higher value. So what we are seeing is the rate of change in lake water levels is negative for very few lakes. So there is like a lake here in the southwestern United States, another one here in Brazil, there's one around the Aral Sea, and then one here in the Middle East, where we have a rate of change in water levels meter per year, very high for the red areas. So we have very high in the Indian subcontinent, in Asia, in North America. It looks like most of the lakes are stable, although we do have a somewhat a red pink one here. In between Brazil and Paraguay, we have a red one here. We have some in South Africa. And so that's a pretty useful map in terms of the significance of it. Where we are seeing a large change in that significance is pretty well distributed throughout the planet. Although, like in Russia, most of it is the rate is the p-value is smaller. Or actually it's higher, but it's not as significant than, for example, in the Arctic. We are seeing that the p-value is actually pretty high in the Arctic. So in summary, the present distribution and prevalence of global rivers and lakes is governed by multiple factors related to both the origin and progression of these water bodies over time. Past and ongoing geologic, climatologic, physiographic, and geomorphologic characteristics and processes are largely responsible for the initial shape of lake depressions and river channels. After their formation, hydroclimatic and landscape factors within the contributing drainage basins determine the hydrological cycle and thus the fluxes of water and sediments into and out of rivers and lakes, which cause continuous and dynamic transitions in their form and properties. Estimates show that there may be more than 24 million kilometers of interconnected rivers with mean annual flow of greater than 100 liters per second, draining the Earth-land surface. River density is highest in wet tropical climates, including the Amazon and Congo basins, as well as colder landscape in the north. Rivers account for only an extremely small amount of 0.005% of all freshwater stocks on Earth, but are major transporters of dissolved and particulate matter from the land to the sea. Stream flow. Stream and river channels, former river channels. The global land surface is covered by an estimated 21 million lakes, with a total storage volume of about 183,000 kilometer cubed. Lakes are ubiquitous in informally glaciated regions where countless depressions were created that filled with water, foremost in the subarctic and temperate regions of the northern hemisphere. In contrast, particularly large and old lakes can be found inside tectonic rifts such as Lake Baikal of Russia and the African Rift Valley lakes. About 2/3 of the total volume of freshwater lakes is contained in only the 4 largest lakes: Lake Baikal, Lake Tanganyika, Superior, and Malawi. Most lakes are much smaller, however, and relatively shallow, less than 10 meters in depth. Natural lakes are formed by either relatively fast catastrophic geological events or by more gradual processes. They can be grouped into several main types of origin: glacial lakes, tectonic lakes, volcanic lakes, landslides, river activity, coastal lakes, solution lakes, wind erosion lakes. More rarely, a lake can be formed in a depression caused by the impact of meteorite lakes. Natural lakes can also have organic origins, such as lakes created by the damming action of plant growth and associated with detritus, or the activity of animals, in particular beavers. After lake formation, succession processes start to fill the lake with the influx of river sediment and the accumulation of organic matter that grows in the lake. The succession process may be accompanied by different stages of nutrient loading: oligotrophic, mesotrophic, eutrophic, and hypereutrophic. There is a great variation in lake morphology. Most water bodies of lakes approximate an elliptic sinusoid shape. The mean depth of lakes on average is about half 0.46 of the maximum depth. The morphology of a lake's water body has profound effects on nearly all physical, chemical, and biological properties of the lake. The morphometry of the lake and the geological substrates of the drainage basin influence sediments, water interaction, and lake productivity, especially that of extremely productive littoral communities. The greater productivity of small, shallow lakes is usually correlated with the higher water sediment interface area per water volume. Reservoirs are appointments created by humans through the damming of river valleys. These dams act as barriers and fragment the connected network of naturally free-flowing rivers. The retention of fluvial sediments in reservoirs can have far-reaching consequences on downstream river morphology. If one includes small farm ponds, reservoirs have been estimated to be in the millions, with a total water storage capacity of over 7,000 kilometers cubed. Given their purpose to store and release water for specific purposes, reservoirs are typically more dynamically fluctuating systems than lakes. Where high rates of sedimentation exist, reservoir or small farm ponds can be very short-lived. Besides the anthropogenic effects of reservoir construction, climate change is expected to both create new lakes, for example, through permafrost melting, and to remove lakes, for example, through desiccation caused by drier or hotter climate. So this concludes Chapter 4 of Wetzel's Limnology textbook, and I'll see you soon for Chapter 5. Thank you.